Hello and welcome to the MOOC lecture series of the RIGHTWEIGHT project of Interact Northwestern Europe. My name is Ahmed Elmahdy. I'm a research engineer and European adhesive specialist at Flanders MAKE in Belgium, and I'm very pleased to give you an introduction to the adhesive joining technology in this educational module. Since adhesives are used in almost every application, as we will see in a moment, this education module will be very useful for a variety of audience. So whether you're an engineering student in any discipline, whether you're a product designer, a manufacturing engineer, or even an adhesive enthusiast or hobbyist who wants to know more information about adhesives that you can implement in your next project, this MOOC is for you. In this MOOC we will cover the following topics. So first, the advantages and challenges of the adhesive joints, the adhesive joining process and its elements, adhesive joining design considerations, quality control in adhesive joint production, and finally debonding of adhesive joints. By the end of this module, you will be able to answer the following questions. Are adhesives suitable for my application? How can I select a suitable adhesive for my application? What are the correct bonding procedures that I need to follow to produce a good adhesive joint? How should I design my adhesive joint to withstand the applied load? How can I test and certify my adhesive operators and my adhesive joint? And finally, how can I debond the adhesive joints? Okay, so let's start with the adhesive joining technology and define what is adhesive joining. So adhesive joining is basically joining two parts together using an adhesive. And this technology is widely available in various industries and various sectors. So for example, you can see it in the transportation sector for bonding, with bonding of the chassis components, windows, windshields, dashboards, and so forth. Also in the energy sector, you can see it with the bonding of the two parts of the wind turbine blades. You can also see it in construction with extensive use of sealants, for example. And you can also see it in packaging and also the do-it-yourself activities. We can see a lot of advantages for using adhesives in comparison with standard mechanical connections or welding. For example, the load transfer in adhesive joining is much more uniform, and any material discontinuity or stress concentrations due to holes, for example, are simply reduced. Also, adhesive joining can offer more functionality. For example, you can have sealing or flexibility or vibration damping with your adhesive joint. In addition to that, also mostly all materials can be bonded with adhesive joining, and you can also bond dissimilar materials together. Of course, with adhesive joining, you don't need bolts or nuts, so you gain a lot of weight reduction by using adhesives. And of course, you can bond very small or very large areas with adhesives in a seamless way. However, with all these nice advantages, there are also some challenges to adhesive bonding. Bonded joints have limited resistance to high temperature, depending on the type of the adhesive used. You can see an example of a typical two-component epoxy in the first graph. The maximum strength is achieved at room temperature, but for example, at much higher temperatures, at 100 degrees, you see a significant reduction in the strength of the adhesive. Also, adhesive joints can age with time and environmental conditions. And as you can see from the second curve here, when the adhesive joint is exposed to higher temperature and water, so in that case it would be humidity, you can see also a significant reduction in the strength after a certain time. In addition to that, adhesive joining is generally a complex process which requires multiple steps, and you also need to do preparation of the part. You also need to do surface cleaning and treatment, and these all also need quite a lot of attention. Adhesive joints are also permanent in nature, so once the adhesive is cured, it would be difficult to debond. But later in this MOOC, we will see some examples on how we can debond these adhesive joints. Finally, adhesives and the associated cleaning agents are considered as hazardous material. So you will see that mostly all adhesive materials will bear one of these spectrograms. safety pictograms. So, but of course, if these materials are handled with the proper safety procedures, the health risk will be significantly reduced. Now let's move to the process of the adhesive joining and see how it is done. We can divide the complete process into 5 main stages. First stage is the preparation of the part and conditioning, where you bring the parts and the adhesives to room temperature and also inspect them for fit, whether they have any faults, also check the tolerances and so forth. Then comes the second part, the second stage, which is surface treatment. And in this process, you want to increase the surface energy of the part, so as to allow it to receive the adhesive. Third stage is the mixing of the adhesives, calculating the correct dosing, and applying the adhesive to the treated surface. Then the fourth stage would be to assemble the parts together and fix it for a certain time and prepare it for curing. The fifth stage would be the curing of the adhesive, and this can be done in an oven or in room temperature, as we will see in a moment. And finally, you have a high quality bonded part. So let's dive into each of these steps in the next slides. Of course, we have to start first with the adhesives. And adhesives are actually polymers that are made up of a group of molecules connected together. Adhesives are mainly consisting of a resin and a hardener material. And if we want to classify the adhesives, we can classify them into 4 main groups. First is the thermosets, which are very strong and very brittle, means that it doesn't have a lot of elongation at failure. And examples of these are epoxies, polyurethanes, acrylics, phenolics, anaerobic adhesives, and ultraviolet curing adhesives. Second category is thermoplastics, which are tough and ductile. And examples of these are hot melts, cyanoacrylates, plastisols, water-based adhesives, and solvent-based adhesives. Third class is the elastomers, which is very, very flexible, and examples of these would be silicones, silane modified polymers, or in short SMPs, and reactive hot melts. And finally, we have the thermoplastic elastomers, which is a combination of thermoplastics and elastomers, so they are strong yet very flexible. And an example of these would be the TPE, or thermoplastic elastomer adhesives. Now, if we classify the adhesives in terms of strength versus ductility, we would see that epoxies, polyurethanes, and phenolic adhesives would have the highest strength, while silicones and SMPs will have the lowest strength but higher flexibility among the adhesives, among all the adhesives. Of course, there are certain chemical formulations which allow the epoxies, for example, to have more flexibility. So in this case, the selection of the adhesive material is dependent on the application and also on the material that you would like to bond. Next step in the adhesive joining process is the surface treatment. Here, the main objective is to improve the surface wetting and long-term stability of the bonded joint. In other words, we would like to prepare the surface to accept the adhesive and have a proper bonding. This is done by increasing the surface energy of the adhesive of the surface, and allow for more spreading of the adhesive onto the surface, which we call wetting. As you can see in the sketch up top, the difference between a bad wetting and a good wetting if you apply the adhesive. So when we treat surfaces for bonding, the main goal is to remove any contamination and expose the base material. So these contaminations can be in the form of oils, fingerprints, moisture, oxides, or silicone layers. One important thing to mention is that once the surface is treated, it's cleaned and treated, you would never ever allow to touch the surface. Otherwise, you will end up with a bad quality of bonding. To clean the surfaces, we use normally cleaning agents or solvents. And here for metals, for example, we use organic solvents like acetone or alcohols, for example. Also, ultrasonic cleaning baths can be used, and so forth. For polymers, we use less aggressive solvents like isopropyl alcohol, so as not to react with the polymer or the plastic in that case. Surface treatment can be done in different ways. So, for example, we have the grid blasting or sanding. We also have plasma treatment, which is more suitable for polymers, and primers and coatings, which are a bit more suitable to painted metals. Of course, the selection of these methods will depend on what is the condition and the material that you would like to bond. Next step is the mixing and dosing of the adhesives. Mixing is actually required when you have two component systems or one component system with a catalyst, for example, like the polyurethanes with booster systems. Here it's important to follow the exact mixing ratio that is stated in the datasheet, otherwise you will end up with incomplete curing. And of course, it's important to calculate the correct dose of your adhesive before the application, so as also not to use or waste too much adhesive in the process. Mixing itself can be done with static mixers, as you can see in one of these in the last image, or for more continuous bonding process, we use industrial dynamic mixers. The final step of the adhesive bonding process is the curing of the adhesive. And by curing, we mean building cohesive or cohesion strength in the adhesive, or in other words, changing it from a viscous liquid into a solid phase. And curing can be done in a variety of ways. First, we have curing by heating. So heating can be done in the oven, or it can be done by exothermic reaction at room temperature. This is specifically for two-component systems. Examples of adhesives that cure by heat are one-component and two-component epoxies, two-component polyurethanes, two-component MMAs, and also phenolic adhesives. Second type of curing can be with cooling. So in that case, would be cooling from room temperature, cooling to room temperature from higher temperatures, and this is associated with hot melt adhesives. Third is curing by humidity, in which the adhesive actually absorbs the humidity from the air and starts a chemical reaction to cause the curing. Examples of these adhesives would be the one-component polyurethane, cyanoacrylates, and also one-component silane-modified polymers. Fourth is curing by evaporation. So this means curing by loss of solvent or loss of water. And examples of these adhesives would be the polyvinyl acetate, or in short, the wood glue, also solvent-based acrylics and polyurethanes. We also have special curing adhesives that cure by different methods. First, we have the anaerobic curing, which is actually a process that happens in the absence of oxygen and also in the presence of metal ions. And you find these adhesives in thread locking adhesives, for example. Another special curing process would be the sol gel curing, in which the adhesive changes from liquid to gel by absorbing plasticizers. And also this process happens in the presence of heat. An example of these would be the PVC plastisol adhesives, which are also used in sealing applications. The final curing method would be no hardening, which is basically does not include any phase change, and there is no solidification in that sense. And an example of these would be the pressure-sensitive adhesives. Now, if we look at how long curing takes versus the final strength of the adhesives, we will see that the fastest curing times can be achieved by cyanoacrylates, followed by ultraviolet curing adhesives and hot melts. While the longest curing times are achieved by the polyurethanes and the SMPs. Epoxies in that sense has a kind of an intermediate curing times, but of course it can achieve the highest strength. So in that sense, what is important to note is that there is no fixed curing time for these adhesives. The curing time is actually dependent on the adhesive chemistry, also the environment, the temperature and the humidity of your application, the processing quantities, and also the type of the application itself. Now let's see how to design a good adhesive joint. In terms of designing an effective adhesive joint, we first have to look at the adhesive properties. So brittle adhesives can resist tension, compression, and shear loads, as you see from these little animations, but they have poor performance in cleavage and peel stresses. Flexible adhesives, on the other hand, can resist to a very large extent peel and cleavage forces. So the general rule here is that if you are using a brittle adhesive in your joint, say for example epoxy adhesive, you should design your joint to promote tension, compression, and shear loading, and minimize as much as possible cleavage and peel stresses or peel loading. If your main forces are cleavage and peel forces, then you have to look in the direction of flexible adhesives. So in that case, polyurethanes or SMPs, for example. These are typical examples of joint designs. So first we have the butt joint, which is very easy to apply, but these joints are very poor in terms of resisting cleavage stresses. One solution to do that is to add two parts on top and bottom of the joint and transfer the joint from a butt joint into a double lap or a strap joint. This actually increases the contribution of shear forces into the load transfer and also protect the joints from the cleavage stresses. What's even better is that we can reduce the peel stresses on this joint by tapering the edges of the top and bottom parts. So this way we are reducing peel stresses, we are reducing stress concentrations, and we have more uniform distribution of the stresses. Another easy joint design is the lap shear joint, which is a good option to start with. However, when the load is applied, this joint suffers from additional peel stresses and stress concentrations due to the change in thickness. One way to overcome this is to simply taper the edges of the substrates, or even better, change the joint into a stepped joint or a scarf joint to maximize shear forces and minimize stress concentrations. These two joints, the stepped joint and the scarf joint, are widely used in bonded repair work. Now let's see how can we test the quality of the adhesive joints. Testing and quality control can be divided into destructive and non-destructive testings. For the destructive testing, the most important tests are lap shear tests, peel tests, and aging tests. Lap shear tests determines the maximum force that the bonded joint can take, and this would be in the form of a bonded lap shear joint. Peel test, on the other hand, determines the resistance of a bonded joint to peel forces. These tests are quite standardized in ISO and ASTM norms, as you can see. Aging tests determine the durability performance of the joint in various temperatures, and we can do that, for example, by testing in different humidity and temperature cycles. Non-destructive testing, on the other hand, give information about the quality of the bond and determine, for instance, if we have air trapped into the adhesive, or if there are some unbonded parts in the joint. The most popular methods are, of course, the ultrasonic testing and thermography. In ultrasonic testing, you use probes that can send and receive ultrasonic waves, and there you can detect changes in media and detect whether you have unbonded parts or not. Same principle with thermography, where you heat your joint with a heating source. In that case, could be a halogen lamp, and take images with the infrared camera, and the difference in media would affect the heat transfer, and this can be detected by the heat image that is produced. Another point is the qualification of the workforce. So proper training of the adhesive of the personnel in the adhesive joining work is very important to produce high quality bonding solution. Also, if you are working with certain standards, like DIN standards, for example, they dictate a certain level of training for the personnel. According to the European Welding Federation, there are 3 levels of qualification for adhesive or personnel involved in adhesive bonding work. First level is European Adhesive Bonder, or in short EAB. And this is specific training for operators who are actually performing the bonding work manually. The next level is the European Adhesive Specialist, or EAS. And these are trained people to supervise the bonding work and also draw up the bonding instructions for the operators. And the highest qualification level is the European Adhesive Engineer, or EAE, which is more of a decision maker and supervises the company-wide bonding application in the joining process. Okay, now if you want to consider adhesive bonding in your company or in your application in general, what are the things that you need to consider when you want to approach this implementation of your adhesive joining? So I picked 5 main aspects that you need to consider when you want to implement the adhesive joining in your next project. First is the application. So you need to consider your application. Is it feasible to use bonding in your application? What is the part and the joint design that you would consider? Also, what are the service conditions of your application in terms of temperature, humidity, for example? And this will, of course, dictate what is the type of the adhesive that you will use. Second aspect would be production constraints and environment. So what are the production times, which of course will dictate how fast the curing needs to be. Also, what are the workflow conditions in terms of temperature, humidity, if there are existing, what are the existing operations and handling processes that you use, whether you need to change these, and so forth. Third aspect is the bonding infrastructure and storage. So of course you need mixing and dosing equipment, you need surface treatment equipment, you need ovens, of course, depending on which application or which adhesive that you are using. You also need proper storage for bonded parts and, of course, the adhesives. The fourth aspect is safety and cleanness. So, of course, you need kind of a dust-free bonding area, also free of silicones. And you also need to have proper storage for flammable solvents. And finally, the aspect of training of the personnel. So of course you need to anticipate training of your workforce into bonders, supervisors, or adhesive engineers. Now, if you remember, we mentioned that adhesives are permanent in nature and it's difficult to debond once the adhesive is cured. In this part of the MOOC, we will have a look at state-of-the-art techniques that can be used to debond adhesive joints. First, when we talk about debonding, we mean disjoining or disassembly or separating the two substrates from each other and from the adhesive. And this can be done either by cutting into the substrate itself, which is what we want to avoid because you want to reuse the substrates afterwards. Or you can do this debonding at the interface between the substrate and the adhesive layer, or inside the adhesive layer itself. The last two methods, debonding at interface and debonding inside the adhesive layer, are the two main focus in this MOOC module. Now, if we look at the different debonding mechanisms, how debonding can be achieved, it can be classified into three main mechanisms. First is mechanical debonding, where you simply apply force onto your joint, and there you can produce cracks which can propagate into the adhesive layer and cause the separation of the substrates. Second mechanism is thermal, where you heat up the adhesive above a temperature called glass transition temperature, and at this temperature the adhesive would change from a glassy state, a hard state with a higher strength, into a rubbery state which is low in strength. So if you apply forces at this stage, the separation can happen and you can have debonding. The third mechanism is electrochemical methods, where you can, for example, apply electrical potential or ultraviolet light to trigger the adhesive to cause debonding. In this MOOC, I will focus on 6 example technologies that can be used for debonding, and they are mainly thermal in nature. We have the convection heating, induction heating, microwave heating, and electrically debondable adhesives, also debonding by thermally expandable particles, and ultraviolet debondable adhesives. Debonding by convection is the simplest debonding method. It simply involves heating the adhesive above the glass transition temperature and applying force while the adhesive is still hot. This way you can have separation of the bond. The main advantages of this technology is that you can virtually use it for any adhesive, because they are all, or most of them are debondable by heat, and you don't have to add any special additives to the adhesive to cause this debonding. However, substrates should be thermally conductive, and of course this is not a local heating method, although you can use local heating methods by convection. But if you have big assemblies, for example, you have to put the whole assembly into the oven, and there you risk introducing thermal stresses into your assembly. Debonding by induction is done by exposing the joint to high intensity alternating magnetic field, which heats up the adhesive by combined effect of Joule effect and hysteresis losses. And this heating can be done also to a temperature above the glass transition temperature, and then by applying force you can debond your substrate. The most advantageous aspect of this method is that it can produce very high heating rates, so you can do this debonding in a matter of seconds, really, and it can provide local heating method. So you don't have to risk, for example, introducing thermal stresses into your assembly. However, this method works only with ferroelectric or ferromagnetic substrates. So in that case, if you have non-metallic substrates like plastics or composites, for example, you have to modify the adhesive by adding conductive particles into the adhesive. And of course, when we talk about adding particles into the adhesive, the mechanical performance of the adhesive would be affected, mostly in a negative way. So this has to be kept in mind when also choosing the right amounts of particles that can be added to the adhesive. Thermally expandable particles is also another interesting debonding method, and these particles are actually made up of a liquid hydrocarbon encapsulated in a polymer shell. When these particles are heated, the liquid hydrocarbon changes into gas and expands the whole particles, and the volume can actually increase even to more than 5 times its initial volume. When you mix these particles into the adhesives, they can actually cause cracking of the adhesive or even reduce the mechanical performance of the adhesive, and that can cause also debonding. yeah, the advantages of these of this method is that you can use any heating method to trigger these particles to expand, and you can also combine certain heating methods. So, for example, you can use induction technology with this method, so you can gain or you can achieve high heating rates for this heating. This method works only with heat conductive substrates, and also we have to take into consideration that there is a certain triggering temperature for these particles, so it's mostly suitable for room temperature curing adhesives. Of course, when we talk about particles mixed with adhesives, that means that also the mechanical performance would be affected in that case. Next, we have the debonding by electrically debondable adhesives, and these are actually special adhesives, specially developed by a laboratory in the United States called EIC. And the idea is that by passing an electric potential across two metallic substrates bonded with this special adhesives, these special adhesives, you can have instantaneous debonding at the anode side. Of course, these are special adhesives, so the commercial availability is a little bit limited by the quantities supplied by EIC, so it's a little bit difficult to get. And it only works with conductive substrates. Of course, there are certain solutions. If there are non-conductive substrates, there are pre-bonded patches made up of this adhesive sandwiched between two conductive substrates, and then this complete patch can be bonded to your non-conductive substrate. Next, we have debonding by ultraviolet light, and these are also special adhesives developed using switchable molecules that can be triggered by certain wavelengths of light to cause debonding or even rebonding in that case. Yeah, these are also limited commercially, but they are available for certain sectors like semiconductor sectors and medical industries. But when we consider structural adhesives, yeah, these are not really available on commercial scale, and it's still in the phase of research. So in that case, it has a low technology readiness level. And of course, one thing to mention is that it works only with transparent substrates. Finally, we have debonding by microwaves, and the principle is basically debonding by dielectric heating for polar molecules, and similar to the induction technology, this can achieve very high heating rates. The advantages of this method is that yeah, it can be used with mostly all adhesives, because all adhesives are actually have polar molecules. But it cannot work with metallic substrates, because then you risk either having an arcing effect or a shielding effect from the microwaves. And of course, it has to work with microwave transparent substrates in order to reach the adhesive and to cause the heating. So if you want to compare, or let's say rank these debonding methods, yeah, actually we combine certain criteria or aspects that we can look for. So, for example, the debonding time, initial bonding strength, how scalable it is if you are considering larger applications, the commercial availability in terms of adhesives or particles, or the combination of both. Also, how safe the method is, how complex the method is, and so forth. And we can see that among these methods, yeah, the three winning methods would be the induction, the convection, and the thermally expandable particles. And yeah, the two runner-ups would be then the electrically debondable adhesives and ultraviolet debonding methods. Yeah. I hope you have enjoyed this MOOC module. If you have any questions or business inquiries, please don't hesitate to contact us on this email. And yeah, thank you for your attention. I will leave you now with some evaluation, self-evaluation questions, and yeah, have a good day.